Light isn't the fastest thing in the universe. Causality is. Everything else we talk about today is what happens when we try to cheat it. Faster than light is the wrong question. When people talk about fast light travel, they usually imagine speed, bigger engines, stranger fuels, stronger materials, some future breakthrough that finally lets us outrun a beam of light the way jets once outran sound. But that framing is already wrong. The speed of light is not a technological barrier in the ordinary sense. It isn't something we might overcome with enough thrust or clever engineering. It's not a limit imposed by friction, drag, or energy loss. Quite the opposite. For objects with mass, it's the accumulation of energy itself that prevents them from ever reaching it. As an object accelerates closer to light speed, each additional unit of energy produces a smaller increase in velocity. You get diminishing returns that grow worse the closer you get, because all that added energy has to be pushed along too. Not just the original mass of the object, but the energy you've already invested in accelerating it. Reaching the speed of light will require infinite energy, not because the universe is stingy, but because of how space-time itself is structured. Only objects with no rest mass, like photons and probably gravitons, can travel at light speed. Even the name is misleading. We measure light first, but this isn't really a speed of light limit at all. It's a limit on cause and effect, and how quickly influences can propagate through the universe. That distinction matters. It's why it doesn't actually matter that some things move away from us faster than light, indeed most things. Because of cosmic expansion, sufficiently distant galaxies recede so quickly that no signal can ever cross the growing gap between us. Not now, not ever. We see only the last fading light from a time when the universe was smaller and causal contact was still possible, while anything beyond the cosmic horizon is forever outside our ability to influence or be influenced by. Fundamentally, light doesn't just tell us how fast things move, it tells us what can cause other things to happen. And that's why fast light travel has always been tangled up with time travel, paradoxes, and causality nightmares. It's not that physicists lack imagination. Indeed, we'll see how inventive many are as we review attempted FTL loopholes today. Nor is the universe is arbitrarily cruel. It's that the moment you allow anything, information, particles, or spacecraft, to outrun light, you aren't just moving faster, you're reordering cause and effect. Nearly every serious proposal for fast light travel reflects this, whether it admits it or not. Warp drives don't break the speed limit, they move space-time itself. Wormholes don't outrun light, they bypass the distance light would normally have to travel. Quantum effects flirt with the edge of the rules without crossing them. And in every case, the same problem resurfaces. If you arrive somewhere sooner than light would, then somewhere, to someone, you arrived before you left. That's the real question behind fast light travel. In this episode, we are not asking how fast we can go. We're asking how space-time responds when we try to cheat its most fundamental rule, and why every shortcut seems to come with a cost far stranger than fuel or engineering. To answer that, we're going to work our way through every serious fast light idea physicists have proposed. We'll start with space-time engineering, warp drives, wormholes, and higher dimensional shortcuts that try to beat light by rearranging the universe itself. Then we'll look at FTL as infrastructure rather than propulsion, where shortcuts are built slowly and used forever after. Like wormholes, we'll examine rare natural loopholes allowed by general relativity, hypothetical particles that always outrun light, like tachyons, subtle vacuum effects that bend causality by microscopic amounts, and quantum near misses that look like shortcuts but are not. And finally, we'll ask why the universe seems so determined to prevent any of these from becoming stable, reliable, or safe. It is a huge topic, and we'll have to skim some of them. Indeed, many have their own whole episodes deep diving them in greater detail. But even with skimming, we're going to be here for a while, so grab a drink and a snack, hit those like and subscribe buttons and the notification bell, and let's dive in. Space-time engineering, moving the map instead of the ship. If outrunning light directly turns cause and effect inside out, the obvious next idea is not to go faster, but to stop racing light altogether. If the speed of light limits how fast objects can move through space-time, then perhaps the solution is to rearrange space-time itself. Instead of pushing a ship across the map, you move the map under the ship. Let distances shrink, let space flow, let the universe do the moving while the spacecraft stays safely within the local speed limit. This is the central insight behind the most famous family of fast light ideas, space-time engineering, often called geometry cheats. These concepts don't try to break relativity, they try to exploit it. In all of them, nothing locally exceeds the speed of light. Inside the ship, physics behaves normally. Clocks tick at ordinary rates. No photon is outrun the ship's immediate vicinity. The violation happens globally, in how spacetime is shaped between departure and arrival. The canonical example is the warp drive. Warp drives, surfing spacetime. There's quite a few variants on this, but the most widely known version currently discussed much is the Alcubierre warp drive. Instead of accelerating a spacecraft forward, it contracts spacetime in front of the ship and expands it behind. The ship sits inside a warp bubble, floating freely, never locally accelerating. To an outside observer, the bubble itself can move arbitrarily fast, carrying the ship along with it. On paper, this works. The spacetime metric satisfies Einstein's field equations. No local physics law is violated. The ship experiences no crushing forces. From a purely mathematical standpoint, it looks like a clean workaround. But the devil is in what the equations demand. To create that warp bubble, the equation of general relativity make a very specific and very difficult demand. Spacetime must contain regions of negative energy density. While that term might sound mysterious, it is simply the opposite of what we see every day. In our world, every atom of matter, every passing photon, and every invisible neutron adds the energy density of a region. It makes that space heavier or more crowded. On the extreme end of this positive density, you have black holes. On the other, the near-empty void of intergalactic space. Personally, I'm skeptical that negative matter, particles with negative mass, actually exists in our universe. But the concept is worth exploring because all physical constraints, like the speed of light, are specific to our corner of the cosmos. Modern physics, particularly string theory, suggests a landscape of potentially billions and billions of other universes, each with its own laws and constants. Many suggested workarounds to the light speed limit rely on finding ways to tap into those different rules. But before we look at other universes, we have to look at the nothing in our own. Even empty intergalactic space isn't truly empty, even if we could somehow block out every stray photon and neutrino. As we explore in our episode on vacuum decay, the vacuum is a bubbling sea of virtual particles popping in and out of existence, a baseline state of energy often called the quantum foam. To understand negative energy, imagine our universe's vacuum state as sea level. We treat sea level as zero altitude, but there's still an entire ocean of depth beneath it. If you want to achieve negative altitude, you have to go below the baseline, which in this case is semi-arbitrary. In this context, negative energy density isn't just an empty room, it's a room that's been emptied of more than nothing. It's a region where the energy state has been pushed below 0 point of the vacuum, or our vacuum anyway. Now, we actually have proof this is possible through the Casimir effect, where the vacuum energy between two close plates is restricted, creating a localized negative density. See our 0 point and vacuum energy episode for a clear explanation. However, and this is a big however, that microscopic quantum dip below sea level is not the same thing as the exotic matter usually discussed for warp drives. Casimir experiments demonstrate local negative energy density under strict quantum constraints, not a stockpile of negative mass material you could shape, gather, or scoop into an engine. When physicists talk about warp drives, they usually aren't talking about plates, they're talking about negative mass matter. This would be a hypothetical substance that possesses negative mass and energy properties, parallel to how we have positive and negative electric charges. It wouldn't just be weird matter, it would be matter that falls up and pushes away rather than pulling in. Despite decades of searching the heavens with our most sensitive instruments, we have never detected a single atom of negative matter. Furthermore, if such matter exists, the scale of the requirement is staggering. Early estimates for the Alcubierre drive suggest that to move a small ship, you would need an amount of negative energy equivalent to the mass of the entire planet Jupiter, all of it compressed into a shell thinner than an atomic nucleus. Later refinements by physicists like Chris van den Broek and others helped reduce these numbers, sometimes by dozens of orders of magnitude, through clever shaping of the bubble and the use of micro-pockets of space. But even with these mathematical discounts, the core conclusion remains. The problem isn't just the type of energy required, but the density and precision of its application. Now, this brings us to an important distinction in theoretical physics. When a physicist says the math works, they are not offering a blueprint for a shipyard. They are stating that the equations of general relativity are flexible enough to allow for such a shape. But nature is under no obligation to provide the exotic materials, the astronomical energy levels, or the structural stability required to turn a valid equation into a physical reality. In the world of FTL, a consistent solution is often just a very elegant way of describing an impossibility. Even if we solve the energy requirements, we'd face the Alcubierre shotgun effect. A warp bubble acts like a gravitational snowplow. As it moves through the interstellar medium, it sweeps up every stray atom, cosmic ray, and bit of dust in its path. These particles don't just hit the ship, they get trapped in the high-energy bow wave of the bubble. When the ship arrives at its destination, and the bubble collapses, all that accumulated energy, now accelerated to insane relativistic speeds, is released in a forward-facing beam of gamma radiation. It wouldn't just be a landing, it will be a stellar-scale demolition charge. Then there's the horizon problem. Inside a warp bubble, the leading edge of the distortion is moving faster than light relative to the ship inside. This means no signal you can send can ever reach the front of your own bubble to steer it or turn it off. You're effectively trapped in a box where you can't touch the controls once the engine is engaged. It suggests that a warp journey might not be a flight so much as a preset ballistic launch into the dark. And the Alcubierre drive is not unique. Soon after its publication, other warp geometries appeared. Notario drives modified the expansion and contraction pattern. Vandenbroek showed that a warp bubble's external footprint could, in principle, be made arbitrarily small while hiding a much larger interior volume. These variations demonstrate something crucial. Warp drives are a class of solutions, not a single idea. But none of them escape the same fundamental trade-off. They all require extreme manipulation of space-time itself. They all demand global control rather than local thrust. And once the geometry allows arrival sooner than light would through normal space, the causality problems outlined earlier return immediately. Wormholes, shortcuts with the side of time travel. Now, wormholes attack the problem from a different angle, but with the same underlying logic. Instead of moving space around a ship, a traversable wormhole connects two distant regions of space-time directly, and to one mouth exit the other. No need to cross the intervening distance at all. From the traveler's perspective, the journey is short and uneventful. General relativity allows this too, at least mathematically. The equation admits solutions where space-time is multiply connected, and forming tunnels between distant locations. But once again, the price is severe. To keep a wormhole open and traversable, space-time must be threaded with exotic matter possessing negative energy density, again, less than nothing. Without it, the throat collapses faster than anything could pass through. And if a wormhole is stabilized, another consequence appears automatically. If one mouth is moved relative to the other, or placed in a different gravitational potential, the wormhole becomes a time machine. This is not an optional feature, it is built into the geometry. A wormhole that enables fast light travel also enables closed time-like curves. You don't get to choose one without the other. We walked through this recently in our Wormhole Stabilities episode with some specific examples. So, wormholes basically are the cleanest time machines allowed by general relativity, not because physicists want them to be, equations insist on it. As good news, you can't use wormholes to travel back to a time before they were created, assuming you're not using one created during the Big Bang, which might have permitted that. Hyperspace, shortcuts through the bulk. Hyperspace and higher dimensional shortcuts are often presented as something different, but physically they belong in the same family, and shockingly, they also have their own episode. In many modern theories, our familiar three dimensions of space may be embedded in a higher dimensional structure, the same as many 2D images can be embedded into a book full of sheets of paper. Think of an atlas with page after page of maps. If that's true, then two distant points in our universe might be close together in the higher dimensional bulk. A path through those extra dimensions could connect them far more quickly than a route constrained to our three-dimensional spacetime. So think of that book as a cosmic atlas. One page might be a street map of London, the next page is a map of the entire galaxy. By moving a fraction of an inch up through the pages, you transition to a scale where a tiny movement represents light years. Step back down into a different C-scale page, and you've traveled across the world, or the universe, without ever having to move fast in our local three dimensions. Conceptually, this is just a wormhole by another name, though an intra-universe one, not an intra-universe one. Instead of a tunnel through space-time, it is a shortcut through higher dimensions. The same questions apply. Are those dimensions accessible, traversable, and stable? Do they require exotic matter? Can you use them to violate causality? Is there any natural phenomena or element that allows us to interact or reach such places if they do exist? And you can see that Hyperspace episode for a deep dive, but for the record, this is the type of FTL I tend to feel most plausible, as it doesn't seem to violate any known laws or explicitly require exotic matter. Of course, we also have no idea what kind of matter it might require either. More recently, there has been a renewed interest in warp-like solutions that avoid exotic matter altogether. Solitons, the positive energy challenge. One of the most discussed recent developments in spacetime engineering is the class of soliton warp solutions. A soliton is a concept borrowed from fluid dynamics and wave physics. It is a self-reinforcing wave packet that maintains its shape while moving at a constant velocity. Think of a tsunami crossing the deep ocean or a stable vol cloud in the atmosphere. And depending on your theory, particles of matter themselves can be considered solitons. In 2021, physicist Eric Lenz proposed that specific hyper-fast solitons could be constructed out of spacetime using only positive energy densities. This was a theoretical breakthrough because it removed the long-standing requirement for negative mass of exotic matter. No outright violation of known energy conditions was required. The math worked using the kind of matter we actually see in this universe. But the result is important for a very different reason from what many headlines suggested. Removing exotic matter does not remove the fundamental difficulty, it just relocates it. This didn't make the warp drive easy, it just moved from the category of mathematically impossible to physically outrageous. The engineering challenges merely mutated. To create a soliton warp bubble just 100 meters across, roughly the size of a small ship, you would need to condense an amount of normal mass energy equivalent to about 1/10 the mass of our Sun, or 1,000 Jupiter masses. You've traded the need for magic matter for the need for civilization-scale energy control and godlike mastery of space-time geometry. Channel regulars would not be surprised that I do prefer this version, though. Furthermore, even with positive energy, the same global time ordering problems do reappear. The universe doesn't care whether your warp bubble uses negative energy or positive energy. If you beat light, causality pays the price. This is the recurring list of space-time engineering. These ideas are all clever, mathematically legitimate, and they respect local physical laws while exploiting the full flexibility of general relativity. Yet they all run headlong in the same wall: global causality. You can move space instead of ships. You can forward distance instead of crossing it. You can turn the universe into a conveyor belt instead of a road. But the result lets you beat light over long distances. Space-time itself must accommodate that shortcut. And when it does, time stops behaving the way we would expect. In the next section, we'll take this logic one step further. What if fast light travel isn't about vehicles at all? What if it's about building the right shortcuts at once, slowly, and letting civilization exploit them forever after? Because at that point, the danger isn't just paradoxes, it's permanence. The Krasnikov tube. Building a star road. Up to this point, fast light travel has mostly sounded like a vehicle problem. Exotic drives, impossible engines, godlike energy sources. Machines so extreme they feel safely hypothetical. Or would anyway if this wasn't SFIA. But there's a subtler and more unsettling possibility. What if FTL doesn't require fast vehicles at all? What if it's an infrastructure problem? Once you stop thinking about FTL as something a ship does, and begin thinking about it as something space-time is prepared to do, the character of the risk changes. Instead of brief violations of causality tied to individual journeys, you get permanent shortcuts baked into the structure of the universe. This is where the Krasnikov tube comes in. A Krasnikov tube is not to drive. It's a space-time modification laid down slowly by an ordinary sublight ship. As the ship travels outward at near light speed, it distorts the geometry of space-time along its path. The result is a narrow corridor where the return trip can be completed in an arbitrarily short time. The catch is obvious. The shortcut only works in one direction, and only after the long, slow construction phase is complete. You cannot use a Krasnikov tube to make the initial journey faster. It is the ultimate civilizational railroad. The first train takes years to lay the track at sublight speeds, but every train after that arrives almost immediately. Don't think of that as a minor benefit either. I was joking a moment ago about how the scale of these FTL options would seem insane anywhere but on this show, but consider the stakes. Last year we did an episode on galaxy-scale megastructures where we discussed the ultimate limits on colonization and mining. We asked how far our ships could go for the resources they reached could no longer be economically returned due to the effects of Hubble expansion. That expansion effectively limits us to a radius of about 1 billion light-years. However, if even a one-way FTL shortcut like a Krasnikov tube works, that bubble moves out to at least 10 billion light-years. We aren't just talking about a slightly larger territory, we are talking about access to a volume of space containing 1,000 times as many galaxies. That is the difference between owning a neighborhood and owning a continent. But there is a dark side to this permanence. Fast light travel no longer requires repeated miracles of proportion. It requires a willingness to permanently alter the map. A one-off warp jump might destroy itself in the attempt, but a Krasnikov tube persists. It accumulates, and once a civilization begins to rely on these star roads, turning them off may longer be possible. Permanence changes the risk profile. Temporary causality violation is a paradox. A permanent one is a restructuring of history. It changes who bears responsibility. With ship-based FTL, the danger is tied to the traveler. With the Krasnikov tube, the danger is imposed on everyone existing downstream of that decision. Future civilizations inherit these shortcuts and the causality scrambling baggage that comes with them, whether they want to or not. Natural relativistic loopholes, cosmic strings and Tipler cylinders. Up to now, fast and light ideas have involved extraordinary engineering, reshaping spacetime, building infrastructure, or exploiting exotic matter. It is tempting to think that all of these problems arise because we're pushing physics too far, because nature itself simply forbids such shortcuts. General relativity complicates that hope. Einstein's equations don't just describe how spacetime responds to matter and energy. They also admit solutions where spacetime geometry itself allows paths that beat light traveling through ordinary space. No exotic technology required. No warp engines. No megastructures. One of those striking examples involves cosmic strings. We recently did an episode on these, but I rather intentionally bypassed the possible FTL applications. But as a quick reminder, these are hypothetical one-dimensional topological defects, thin, immensely dense remnants that may have formed in the early universe. They don't curve spacetime the way planets or stars do. Instead, they create a conical geometry, removing a wedge of space and stitching the edges together. The result is that spacetime around a cosmic string is globally distorted, even though it may look flat locally. In the GOT solution, two infinitely long cosmic strings pass by each other at relativistic speeds. The combined geometry allows a path where a traveler, or a signal, can loop around them and return faster than a light beam traveling through normal space. Nothing locally exceeds the speed of light, and no exotic matter is required on the cosmic string. The effect emerges purely from the global structure of spacetime, and yet the consequence is familiar. That loop is also a closed time-like curve, a time machine. And while we mentioned that FTL solutions tend to let you do time travel too, it is worth noting that time travel lets you break the speed of light and causality too. Probably. More on that in a bit. A close relative to the cosmic string solution is the Tipler cylinder, first proposed by Frank Tipler in 1974. If the GOT solution is about the geometry of moving lines, the Tipler cylinder is about the geometry of rotation. We know from general relativity that a massive rotating object doesn't just pull on things with gravity. It actually drags the fabric of spacetime along with it, an effect known as frame dragging. In our own solar system, this effect is so tiny it's nearly impossible to measure, but if you take a cylinder of ultra-dense matter, something with the density of a neutron star or neutronium, and spin it so fast that its surface is moving at least half the speed of light, the frame dragging becomes catastrophic. Near such a cylinder, the light cones of objects are tilted so far over that forward in time begins to point around the cylinder. If the cylinder is sufficiently long, a spacecraft following a spiral path around it could enter a closed time-like curve, essentially orbiting a point in its own past. Like the cosmic strings, the Tipler cylinder does not require exotic matter or magic physics, though they might be much easier to make with something like magmatter, theoretical ultra-dense material made from magnetic monopoles, another space-time topological effect like cosmic strings, which recently got its own episode. It only requires mass and angular momentum. However, it also has the same catch. The original math only works if the cylinder is infinitely long. While some have argued a finite cylinder could still work, others suggest the moment you try to build one, the singularity at the ends would create a horizon that prevents you from ever using it as a shortcut. It reinforces the section's theme. The universe allows the loophole in theory, but seems to forbid the construction of the hardware. Another famous example comes from rotating universe solutions, such as those explored by Kurt Gödel. In Gödel's solution to Einstein's equations, the entire universe rotates in such a way that closed time-like curves exist everywhere. You don't need a machine to travel from the past, you just follow the geometry. Our universe does not behave this way. Observations rule out global rotation on anything like the required scale. But Gödel's solution remains important as an existence proof. It shows that general relativity does not enforce causality by default. Causality emerges from the specific structure of our universe, not from absolute prohibition in the laws themselves. Taken together, these examples make an uncomfortable point. Fashion-light paths and time loops are not inventions of science fiction. There are latent possibilities in our best classical theory of spacetime. Physics does not forbid them outright. It merely makes them rare, unstable, or cosmologically extreme. That suggests a deeper pattern. The universe does not necessarily say no. Instead, it seems to say, only under conditions you are extremely unlikely to survive or control. And that brings us to the cleanest thought experiment of them all. Tachyons, the simplest way to break time. If you want to understand why fast light travel so reliably turns into time travel, there is no clearer illustration than tachyons. Tachyons are hypothetical particles that always move faster than light. Unlike ordinary particles, which require infinite energy to reach the speed of light, tachyons require infinite energy to slow down to it. In the mathematics of special relativity, they have imaginary rest mass and behave in strange but internally consistent ways. Again, to no surprise, we have an episode on this too, though it is a very early era SFIA episode, so I speak a good deal faster and my R's are as absent as tachyons are from the standard model. If tachyons exist and could carry information, they would immediately destabilize causality. Because simultaneity is relative, a tachyon emitted by one observer and absorbed by another can appear in a different reference frame to be absorbed before it was emitted. The particle doesn't just arrive early, it appears to move backwards in time. This is not an added feature or an interpretation trick. It is a direct consequence of combining fast light motion with relativity. The equations force the reversal. With two observers moving relative to each other, tachyons allow messages to be sent into the past. With a simple exchange of signals, you construct a closed causal loop where an effect prevents its own cause. No wormholes, no curved spacetime, no exotic geometry, just fast light motion. This is why tachyons are widely interpreted not as real particles, but as signs of instability. In quantum field theory, a tachyonic mode usually means the system is in an unstable state and wants to reorganize itself in a new, stable configuration, where tachyons effectively disappear. Nature doesn't tolerate them, it resolves them. But the concept of time reversal pops up elsewhere in particle physics too. Many physicists, following the work of Richard Feynman and Ernst Stuckelberg, have noted that an antiparticle can be mathematically treated as a regular particle moving backwards in time. Consider pair production, where a particle and its antiparticle appear from the vacuum, only to annihilate an instant later. What we might actually be seeing is a single particle popping into existence, moving forward for a moment, and then being scattered backward to its moment of creation. Because the properties of a particle, like its electric charge, flip when you reverse the direction of time, an electron moving backward in time effectively becomes a positron, its antiparticle. This gives us a profound insight into the FTL problem. Tachyons are the simplest possible FTL mechanism and the fastest way to break time. They show, with brutal clarity, that faster light motion and backward time motion are not separate phenomena. They are the same thing seen from different frames. So, when people ask, what if there's a particle that just goes faster than light, the answer is straightforward. If such a particle could transmit information, the universe would not remain causally ordered for very long. They don't offer a loophole around the problem of FTL. They are the problem, just distilled. Vacuum and time advance effects, when causality bends just a little. Up to now, fast light ideas have failed loudly, requiring impossible energies or universe-breaking geometry. But physics also offers something subtler. Effects that appear to bend in causality just enough to make us uneasy, without letting it snap. One example is gravitational time advance, the lesser-known mirror image of the Shapiro delay, which to be fair is also not well known. To understand the advance, we first have to look at the delay. In 1964, Erwin Shapiro predicted, and later proved, that light does not just curve when it passes near a massive object like a star. It actually takes longer to complete the journey. This isn't because the light slowed down locally, but because gravity stretched the distance it had to travel. We've measured this delay many times by bouncing radar signals off of planets, and it's foundational proof of general relativity. Gravitational time advance is the mathematical opposite. In certain theoretical configurations, particularly involving those regions of negative energy we discussed earlier, signals could arrive earlier than they would in empty space. In this scenario, the geometry of space is not stretched, it's effectively compressed, allowing a signal to reach its destination ahead of schedule. The same is true of the Scharnhorst effect, which predicts that light traveling through the narrow vacuum gap between two closely spaced conducting plates can move slightly faster than the usual speed of light in empty space. If this reminds you of the Casimir effect, it is the same principle. Those two plates prevent the formation of any virtual particles whose wavelengths are larger than the separation between the plates. Imagine it like a filter. No long radio waves or microwaves can pop out of the vacuum where the plates are only micrometers apart, because they're just too big. This means slightly less quantum foam is seething in that gap, resulting in a lower energy density locally and a slightly faster propagation of light. However, we shouldn't get too excited. Light is barely slowed by the quantum foam anyway. It isn't like light traveling through glass or water where the speed drop is significant. More importantly, simply changing the propagation speed of light through a medium, even a modified vacuum, does not automatically allow for time travel. Light travels slower passing through our air than it does above the atmosphere, and not trivially either, but this difference still doesn't allow time travel. Nothing locally exceeds the true speed limit of causality. No causal rule is violated in the immediate neighborhood, and yet, compared to the flat space path, the signal arrives ahead of schedule. This is real physics, at least mathematically, but is also vanishingly small. The effect exists, but it scales so badly that it's effectively a rounding error in the universe's bookkeeping. That said, if we could imagine a nanometer-scale Casimir plate wire stretched toward a sensor several light years away, it might just give you a fraction of a second's head start. It wouldn't let you call home to the past, but it might give you just enough time to cycle your defenses against a supernova's light or an incoming Nyquist beam. It's a microscopic cheat, but in a universe of hard limits, a millisecond of warning might be worth more than a fleet of sublight ships. Variable speed of light theories take this idea to a more speculative extreme. Some cosmological models propose the speed of light was higher in the early universe or varies with vacuum structure. These ideas are usually invoked to address problems in cosmology, not transportation. Even if true, they don't offer a dial we can turn. They tell us something about cosmic history, not how to send a message faster tomorrow. Unless, of course, they do. Theory comes first. Technology that utilizes it cleverly comes later and often surprises us. It is entirely possible that the speed of light or the gravitational constant can be locally dialed up or down with magical ease if you have sufficiently advanced technology, what we usually call clock tech. Needless to say, taken together, these effects make an important point. Physics doesn't treat the speed of light as a sacred, untouchable number. It treats it as an emergent property of spacetime and vacuum structure. Under extreme conditions, it can bend, slightly. But scale matters more than existence. Tiny causality violations are tolerated because they do not compound. They do not form loops. They do not allow information to outrun its cause in a way that can be amplified. The universe seems willing to permit microscopic cheating, but not macroscopic shortcuts. The pattern should feel familiar by now. Whenever faster light travel comes up, a particular set of quantum ideas gets invoked as possible loopholes. This section exists to close those doors cleanly. Let's start with quantum tunneling and the so-called Hartmann effect. In some experiments, particles appear to traverse a barrier faster than light would cross the same distance in free space. This sounds dramatic, but what's actually happening is wave packet reshaping. The peak of the wave exits early, but no usable information travels faster than light. You can't send a message this way. The effect is real, but it is not a shortcut. The same goes for phase velocity versus group velocity. In certain media, the phase of a wave, the apparent peak of a pulse, can move faster than light. The group velocity, which carries the actual information energy, does not. No matter how clever the optical setup, causality stays intact. Then there's the most famous misconception of all, quantum entanglement. We have an episode on entanglement from right before that Tachyon episode I mentioned, if you want more details, but let's recap. Entangled particles are pairs that share a single, unified quantum state. The properties of one are instantly linked to its partner, regardless of distance. Measure one and the state of the other is immediately constrained. This sounds like a telephone. That's more like a pair of socks. There's an example I like to give for this. I send you a letter at Alpha Centauri and your sibling one at Tau Ceti. I tell you both that one letter is written in red ink and the other in green. The moment you open your letter and see red, you know instantly that your sibling's letter is green. That information was obtained faster than light, but it's trivial information. You didn't choose the color of your sibling's letter, you just discovered a pre-existing correlation. In quantum mechanics, you don't get to decide whether an entangled particle will be up or down, red or green. It's random until the moment of measurement. And very importantly, the moment you measure them, they stop being entangled. You have used your one-time discovery and you are done. This is formalized in the no communication theorem and it's been tested exhaustively. Entanglement is non-local, but is not acausal. You are welcome to try to think of ways to send information this way, but don't get your hopes up. I and most other physicists I know have spent years trying to poke holes in this to find a way to send FTL signals, and no one has found a trick around it yet. Odds are if you find one, you will soon also find yourself with a Nobel Prize and as a trillionaire. It's an irritating reality of our universe. We know relativity and quantum mechanics work because we test them to a point of exhaustion. They were not popular theories and very smart people worked very hard to try to find flaws in them. Why they work is still a matter of deep debate, but the why doesn't change the that. You're stuck with the results. These quantum effects are fascinating, and they matter deeply for how reality works, but they do not provide a backdoor to FTL travel. They don't even weaken the speed limit, they dance around it without crossing. What they suggest is something more subtle. At the deepest levels, spacetime, causality, and quantum information may be entangled with one another in ways we don't yet fully understand. Quantum gravity may eventually change how we think about distance, time, or locality, but whatever that future theory looks like, it will still have to explain why causality remains so stubbornly intact at human scales. So when quantum mechanics comes up as an escape hatch, the correct response is not dismissal, it's clarification. Quantum physics doesn't give us shortcuts through space-time. It tells us why shortcuts are so hard to build. Civilization does not usually end because one thing goes wrong. It ends because one rare catastrophe arrives before anyone has built the tools, backups, and redundancies to survive it. Ice ages, solar flares, rogue planets, supernovae, lost archives, failed recoveries. These are not just disasters. They are stress tests for whether a civilization has become durable. That is the idea behind my new Nebula Plus collection, Cosmic Catastrophes and Survival. It gathers my Nebula-exclusive episodes on extinction risks, planetary disasters, civilization backups, and rebuilding after collapse. This month's new edition is Nearby Supernovae. Could one destroy Earth, and could we stop it? Where we look at whether exploding stars have threatened Earth before, which nearby stars might eventually explode, and whether a future civilization could shield itself, move the danger away, or harvest the aftermath. If that sounds like your sort of rabbit hole, you can find the full collection on Nebula, along with years of SFA exclusives, collections, bonus episodes, and regular episodes early and ad-free. My link or the QR code gets you 50% off an annual plan, or 40% off lifetime access. Why the universe pushes back. Chronology protection and self-defeating physics. By now, a pattern should be impossible to ignore. Every serious fast-night proposal, whether it relies on engineered spacetime, natural relativistic loopholes, vacuum effects, or hypothetical particles, runs in the same kinds of trouble. Not just engineering challenges, but deeper instabilities, infinite energy requirements, runaway quantum effects, and feedback loops that grow instead of settling down. This has led physicists to suspect that something more than coincidence is at work. The most famous expression of that suspicion is the chronology protection conjuncture, posed by Stephen Hawking. In essence, it suggests that while the laws of physics may permit spacetime geometries that allow time travel or fast-light shortcuts in principle, they prevent those geometries from becoming stable, macroscopic realities. Not by forbidding them outright, but by destroying them as soon as they become dangerous. In many analyses, the moment a spacetime configuration approaches a closed time-like curve, quantum effects explode. Vacuum fluctuations grow without bound. Particle production runs away. The would-be time machine becomes a self-amplifying catastrophe that tears itself apart before it can be used. This is not a proven theorem. It's an inference drawn from repeated failure. But there is an alternative to Hawking's destruction, the Novikov self-consistency principle. This suggests the universe is not a fragile thing that breaks when you introduce a loop. It's a self-correcting one, and not requiring time lords or causality cops. In this view, you can travel to the past, but you find that any action you take was already part of history. You cannot kill your grandfather because the fact that you exist to try proves that you failed. This creates a different kind of protection. Instead of an explosion, you get a locked timeline where free will is the casualty instead of the starship. It's a less violent answer, but for a civilization built on the idea of agency and exploration, it's perhaps even more unsettling. It implies that FTL and time travel don't open the door to a new future, rather than lock us into a pre-written past. Again and again, theories have found elegant solutions to Einstein's equations that permit fast-light travel or time loops, and again, those solutions seem to summon their own undoing. The universe appears tolerant of tiny, isolated violations, but hostile to anything that could be exploited, scaled up, or relied upon. Seen this way, fast-light travel may not be forbidden so much as unstable by design. The key shift here is conceptual. Physics doesn't behave like a rulebook with hard yes and no answers. It behaves like a system with feedback. Push gently and the system flexes. Push too hard and it pushes back, sometimes violently. FTL isn't impossible, it's self-defeating. Understanding why fast and light travel fails teaches us an enormous amount about how the universe actually works. It reveals that causality isn't an arbitrary rule. It's an emergent property that spacetime might actively protect. It redirects our attention away from the cheat codes and back to the past that actually work. Relativistic travel done well long-term planning across generations, and interstellar societies that respect light-speed delays rather than fighting them. A universe without FTL isn't a universe without exploration. It's a universe that rewards patience, foresight, and resilience. We have so many episodes exploring ways to settle space under known science. The deepest limits we encounter are not walls placed in our way to stop us, but contours that shape how progress actually happens. We don't get to outrun causality, but by understanding it, we learn how far and how wisely we can go.